All right, so welcome Tristram, and he'll be speaking on a parametric version of the LLL algorithm and consequences.
Oh, well, thank you, Alexei, Veronica for organizing, and Alicia, if she's there. And so yes, so this is joint work with my colleague John Goodrick from Los Andes in Colombia, and with Kevin Woods from Oberlin College. So let me start with the consequences. So here are a couple of famous problems involving lattices, that is, subgroups of z to the m. If I'm given a lattice, let's say given a basis for a lattice, I want to find a non-zero vector, which is the shortest, that is, has the minimum Euclidean norm. Or a cousin of this problem is the closest vector problem. So here, given, again, a basis for a lattice, and now given a rational vector, I want to find the closest vector or a closest vector to this given x. Now, well, one important thing about these problems is that they're hard. So there are no known polynomial time algorithms for either of these, at least with the dimension varying, and the CVP is even NP hard. So this makes them attractive for cryptography. So not only are they seem to be hard for classical algorithms, people conjecture that they're even hard for quantum algorithms. So people who do post-quantum cryptography try to build crypto systems on these things. That's I'm not going to be talking about that. I don't know that much about it, but it's certainly an application. I'm going to go a different direction, which is something that John and Kevin and I have been thinking about in various contexts. So we're going to take, we're going to parameterize the problem. We're going to have a family of lattices, one for each natural number t. So the way we do this is that we take the generators to have coordinates being polynomials in t. And so now the question is, I take the SVP and the CVP, and I ask, well, how does the shortest vector or the closest vector depend on the parameter t? Well, what kind of function is it? Well, at the least, I mean, the best you could hope is that it might be a polynomial because the input is polynomial. But that's not going to be quite enough. So let's take a couple of very simple examples of the shortest vector problem. So if my lattice, if the tth lattice is generated by the vectors t2 and 1t squared, well, for example, if t equals 0, then I have the vector 1, 0, and that's certainly as short as you can get. If t equals 1, well, my generators are 1, 2, and 1, 1. By subtracting them, I can get 0, 1, which is also as short as possible. If t equals 2, you can try this yourself. You can get the vector minus 1, 2, and nothing shorter. If t is large, well, then this vector 1t squared is going to be long, and any combination that uses it is going to be long. So in fact, for any very large t, in fact, for t at least 3, a shortest vector is just the other basis vector, t2. So this is something that can happen. So the answer is polynomial, but only eventually for t very large. Another thing that can happen, so again, just a two-dimensional lattice generated by constant vector 3, 0 and by a parametric vector 2t1. It turns out that the shortest vector is periodic, depends on t mod 3. Because basically you can use this 3 to kill off most of that big t2t, but not exactly, only if it's a multiple of 3. So we need a class of functions that includes these eventual polynomials and also includes periodic functions. And so I would say that the most natural class of functions, or the minimal class of functions that contains both of these behaviors, is the class of eventual quasi-polynomials. So, okay, I wrote the definition for vector-valued functions, but basically an eventual quasi-polynomial is a function that, for sufficiently large t, begins to oscillate between a finite list of polynomials. If we didn't have the eventual, a quasi-polynomial would just be alternating between n polynomials. And here I'm talking about a vector function, so I mean each component is an eventual quasi-polynomial. So this is the thing that John and Kevin and I have been studying for years and attracted us to the problem. So a lot of people have thought about kind of parametric lattice point problems. For example, Caligari and Walker and Shen were working on integer programming in a parametric polyhedron. So the facets of the polyhedron are varying according to polynomials or something like that. Chen, Li, and Sam were talking more about counting problems, counting integer points in parametric polyhedra. And Woods sort of conjectured a generalization of all of this, which the three of us proved a few years ago. I won't tell you exactly what it means because it's technical, but we basically show that a wide variety of parametric counting and optimization problems that are specifiable in a certain language, which is called parametric Pressburger arithmetic, have eventual quasi-polynomial solutions. So getting back to the topic of this talk, if I told you the definition of parametric Pressburger, it would be an immediate consequence that if instead of the Euclidean norm, if I ask for the shortest or closest vector with respect to the one norm or the infinity norm, or in fact any polyhedral norm, the answer would be eventual quasi-polynomial. But the actual problems we want to solve with the Euclidean norm are not parametric Pressburger, because the Euclidean norm is, well, it's defined in terms of the squares of the variables, and our machinery doesn't allow that. But nonetheless, we're only talking about lattices. The lattices ought to be simpler than polyhedra. And we did some examples, and it looked like this still might work out. So to skip to the end, this is in fact what we proved. So the parametric shortest vector problem and the closest vector problem do in fact have eventual quasi-polynomial solutions. Now, how do we get there? Let's forget about parameters for a minute. Just the ordinary shortest vector problem, given that it's difficult, one thing you can do is to construct approximate solutions, find a vector in the lattice which is fairly short. And the way you do this is to use this definition of Lenstra, and Lovász. So we say that a basis is LLL reduced if it satisfies two conditions. One is that the vectors are roughly orthogonal. That is, if I compute these Gram-Schmidt coefficients, they're all at most a half. And the other condition is a little complicated because it has to do with the norms, not of the vectors themselves, but of the associated Gram-Schmidt vectors. But it tells you that the vectors are sort of not in reverse order. They should be going roughly from shorter to longer as you go along. And it turns out that if you combine these two conditions, then you actually know that the first vector in this ordered basis is a short vector. And not the shortest vector, but its length is within a constant factor of the length of the shortest vector, where the constant factor is 2 to the n minus 1 over 2, so it depends on the dimension, but that's all. And furthermore, you can see from the size reduced condition that the elements of an LLL reduced basis are approximately orthogonal. And in fact, I should say that not just the first one is short, but all of them are short in a certain well-defined sense. So we find a basis of short vectors, roughly orthogonal bases for the lattice. Now, along with the definition and what they proved, is they actually found an algorithm, and it's a polynomial time algorithm to compute an LLL reduced basis. So this is how you can get at least an approximately short vector. So now back to our parametric case. So knowing this, what we wanted to do was essentially to parameterize the LLL algorithm. And this is our other result. So we proved that if we have a parametric lattice, then there exists a set of vectors whose coordinates are eventually quasi-polynomials, and they form an LLL reduced, well, the teeth basis forms an LLL reduced basis for the teeth lattice when T is sufficiently large. So before I talk about how to prove that, let me explain how to get from parametric LLL to parametric shortest vector, because this is not so difficult. It's a neat little argument. So one fact is if I have an LLL reduced basis and V is the actual shortest vector, then I can express it as an integer combination of this basis where all of the coefficients are at most 3 to the n. Another fact, this is probably a little hard to read, but if you think just about polynomials, if I compare two polynomials of T and I let T increase, then one of them is eventually going to be bigger. So if I have quasi-polynomials or eventual quasi-polynomials, then what's going to happen is that the biggest one is going to alternate periodically in some way. That is, there exists a modulus such that if I fix I mod m, I know which function is going to be the biggest for all T which are congruent to I mod m. Mod n. Whoops, I guess m and n are the same here. So now, combining these two things, suppose I have a parametric LLL reduced basis for my parametric lattice with EQP coordinates. So from the first fact, the shortest vector only has so many options. So each coordinate is some number between -3 to the n and 3 to the n. So I only have this number of options for all of the coordinates together. Each one of them gives me an eventual quasi-polynomial. But then by the second fact, the choice of among all these options is going to be eventually periodic. And an eventually periodic choice between EQP functions is again EQP. So this is the shortest vector. We have to do something similar, but quite a bit more elaborate for the closest vector problem that I won't describe. But I want to talk more about the LLL algorithm and how we parameterize it for the rest of the talk. How much time have I got?
Well, 10 minutes total.
Oh, great. So, thanks. So the LLL algorithm really just involves two steps, but you have to alternate them in kind of a complicated way. So one step would be, it would be doing Gram-Schmidt, a step of the Gram-Schmidt algorithm, except that you can't actually use Gram-Schmidt because we're working in the integers. So we round off the coefficients and do essentially the best you can over the integers. And the other kind of step is just to swap two adjacent vectors, because if you don't satisfy the second condition, you might satisfy it by swapping two. The problem is, in trying to satisfy one condition, you can screw up the other one. So the number of iterations of these things and figuring out when you're supposed to swap is a little bit complicated. So it's not even obvious from the definition that this algorithm terminates. It does, it terminates in polynomial time, but this takes some work. That's the meat of their paper, part of the meat of their paper. So what we want to do is find a parametric version of this algorithm. So I replace these BIs by vectors whose coordinates are polynomials in T. So this maybe fits better into this session. So Okay, this is more symbolic now. Why not just work over the ring of polynomials or EQP functions? Well, you need Gram-Schmidt vectors, but that's okay. You can do Gram-Schmidt over the ring of rational functions as long as you don't normalize, which we don't want to do anyway. You can't normalize because that would involve a square root, but we're okay that so far. The second fact is, and this is behind all of this work, this is really why EQP functions are all over the place. It's that if I have a rational function with integer coefficients, rational coefficients, then the floor of that function is going to be eventually quasi-polynomial. So these mu's, these rounded off Gram-Schmidt coefficients would be EQP. So why not just apply the LLL algorithm over Z of t and well over the ring EQP? Well, there are a couple of issues. One is that each time we take the floor, we take a new floor, we're going to be making more quasi-polynomials, and the periods, or the common period, will get bigger and bigger. Now, since we have quasi-polynomials, deciding when to swap two vectors is going to depend on I modulo the common period. So you're going to have to branch the computation each time you iterate. And furthermore, you're going to wind up with denominators, and you have to do variable changes which kind of increase the coefficients as you go along. And we thought about this, and we don't know. We don't actually know if you literally try to follow the algorithm, whether it will even terminate. And even if it did, it would be messy, and it's not clear how things would work. So we do something else. So the idea is, suppose I have a vector of polynomials, like say 2t squared, 2t plus t. If I think about what happens when t is really big, the direction of this vector is really just going to depend on the coefficients of the highest power of t. So in this case, it's t squared. So 2t squared, 2t plus t is almost in the same direction as 2, 0 if t is large. And the second one would be 3, 0. So that's what we do. We look at the highest power of t that occurs in the polynomial, look at the coefficients only of that power, and we call that the pilot vector of a parametric vector. Pilot because it kind of guides the direction. So now the idea is we just do, the first idea, we can do the ordinary LLL algorithm on the pilot vectors. So this effectively tells us some combination of the pilot vectors that gives us an LLL basis. We can express this by writing this. The B's are the pilot vectors times some integer matrix U. Then just apply that same matrix to the whole polynomials, to all of their coefficients. And that almost works because we're doing it on the highest order. We get something which we call asymptotically LLL reduced. But there's some hypotheses here. So this only works if my polynomial vectors are all of the same degree and if the pilot vectors are linearly independent over Q. But this is maybe the most important idea in the proof. What's even better here, we're only doing LLL with ordinary vectors, so there's no branching. We're not creating quasi-polynomials or anything. But there are these issues. So first of all, we don't literally get what we want. Eventually LLL reduced, we get something a little weaker. And then we may not be in this situation. It may be that we started with vectors that are of different degrees, or we might have started with vectors that were of the same degree, but these pilot vectors could be linearly dependent, as they were in my example. And in these cases, that result just does not hold, and then not even close. So you have to do something else. So for the second problem, or I guess the third problem, the linear dependence, if I have vectors of the same degree, I do something else with the pilot vectors. I can use the Hermite normal form to eliminate one of the pilot vectors, which means lowering the degree of the whole vector. So taking the same example, 2t squared, 2t plus t, and 3t squared and 7 with pilot vectors 2, 0, and 3, 0. Well, how would I eliminate one of these leading coefficients? I can subtract the first vector from the second. So that brings the leading coefficient of the second vector down to t squared. Then I subtract twice the second vector from the first one. I do this all just by looking at the leading coefficients. And that eliminates t squared in the first vector. So now I have a degree 1 vector and a degree 2 vector. Now, of course, when I've done that, I totally changed the pilot vector of the first one. So we have to do this first, basically. We've got to get rid of linear dependence. But you know you're only going to do this a fixed number of times, because we start with vectors of some degrees, and each time we do this, we lower at least one of the degrees. So now the other issue, what if I have vectors of different degrees? Well, it turns out then you can use just an ordinary reduction step like this rounded off Gram-Schmidt we take the lower ones and use them to reduce the higher degree one. And we get something actually very strong. We get that the higher degree one becomes almost orthogonal to the lower degree ones. Literally, its pilot vector will be orthogonal to their pilot vectors. Now, this does involve branching, because when we reduce, remember, we're introducing one of these coefficients, which is a floor of a rational function. So when we do this, we have to branch to get back into the ring Z of t that we like. So for an example, let's say there's just one lower degree vector, in fact, a constant vector, 1, 1, and the higher degree is this vector 3t squared and t plus 5. So it turns out that the mu, the Gram-Schmidt coefficient I'd want to use would be this, t squared plus 2t plus 3 over 2. But that's not always an integer. So the f prime is f minus rounded off mu times 1, 1. And so this is a quasi-polynomial of period 2. But you see, no matter which of the two polynomials involved, the pilot vector is 2 minus 2, which is orthogonal to 1, 1. So this is the good thing about different degrees. Because the one is so much bigger than the other, I can reduce to make them really close to being orthogonal. And so now I'm out of time. Let's see.
Maybe it's a great time to wrap it up.
Okay, well, I only have one more slide. It's just putting it all together. No, I'll tell you what, I won't do that. I'll tell you the future directions. So the slide I'm skipping is the algorithm, but it's basically combining the steps that I did and a couple of others. So here are some future directions. So this result says that various things, the LLL reduced basis and the shortest vector, have eventual quasi-polynomial coordinates, but that's kind of vague. We'd like to know how big could the period be in these quasi-polynomials? Or in other words, how many polynomials do we have to alternate through? And similarly, and probably harder based on our experience with other problems, we would like to know how big is sufficiently large. How big does t have to be before we get to quasi-polynomials? Because otherwise we don't know what the answer is at all. And I guess more generally, we know a bunch of things about polyhedra, but not so many about lattices. So what other parametric lattice problems could we treat with this kind of methods? And would we expect eventual quasi-polynomials to show up? So thank you very much.
Thank you. All right, so any quick questions?
So
I have a quick question. Did you have any useful thoughts coming from model theory into this?
Not into this project, but into the sort of the one that motivated us, our general result about parametric Pressburger arithmetic. It has to do with quantifier elimination, among other things, and extending quantifier elimination into a new domain.
Thank you.
So this one, well, no, sorry. Yeah, go ahead.
No, please go on.
This one somehow is not so complicated. I mean, we're basically, because there are no quantifiers in it, so somehow the logic doesn't really come into this problem.
I was going to say something very stupid. So this is when you say bound sufficiently large, is like bounding the regularity. So because when you are doing computations in homological commutative algebra, and you compute Hilbert functions again, a polynomial, when it becomes a polynomial or quasi-polynomial, you have this kind of, I don't know if it has a parallel in considering monomials with these exponents, or if there is some commutative algebra, monomial algebra, whatever correspondence. Probably.
Well, we don't know, but it would be great if there were, because one of the weaknesses both of this result and with our previous work is that we really don't have a good way to get a handle on the eventually. So if we could find some algebra that connected to it, we would love that.
I have no idea. Terminology is similar, not just that.
All right. Any more questions? Okay, thank you.